This tutorial, we're going to set the color of our window to white, and although that may not sound like much, but we're actually going to enable pixel access effectively in this window, which at the moment is black. And we're going to just make sure that the thing's basically working by setting the window to white. Oh, here we go. So we've got a black window at the moment. I've just accidentally started 3 copies of this. And we're going to enable pixel access here and then just make the whole thing turn white, which is quite easy to do before we go on to setting individual pixels. Of course, this isn't strictly speaking an SDL tutorial. It's a C++ tutorial. I'm just using SDL as an example of a graphics API because we need some kind of API. And I don't have all the details of the SDL API in my head, so for that reason I'm going to refer to a finished project that I created by, as I explained in a previous tutorial, looking up tutorials on the internet relating to SDL and then changing a few things by consulting the API, official API documents by searching for function names. So I'm going to kind of cannibalize my own code here and copy it in bit by bit. In fact, I'll type it out and I'll explain as much as I can as we go along. But my knowledge of SDL is not very in depth. I just figured out enough to get this working. So I hope you'll forgive me here for actually copying my own code rather than just speaking from the top of my head. I could have memorized this stuff, but it would have been a little bit sort of fake because I certainly don't know SDL all that well. And by the way, I hope that you'll follow along and after each video implement your own version of this program, either exactly the same or even slightly different. That's a really good thing to do to get the most out of these videos. Otherwise, if you're just watching them, this will kind of never sink into your head, unfortunately. So let's take a look at the program that I actually finished, this particle explosion program, which is down here. I've called it SDL test. And if we go to I've got an object, a class in here called screen, which we're going to construct later on. But first I want to get just a basic main function that just illustrates the kind of basic elements of what we need here. And later on I'm going to refactor it and make it more object-oriented so that we don't get into a tangle when we add more and more code to this. So in my screen class here, I've got an init method, and in here we are creating a thing called a renderer and a thing called a texture. So my understanding here is that the renderer is something we use in SDL to actually draw on the window. We've got a window, but we need a renderer to render stuff, in other words, draw stuff on it. And we also need a texture, which is like a bitmap that we can draw directly to. So we'll be creating the renderer, doing stuff with a texture, and then passing the texture to the renderer, and then telling the renderer to display in the window, basically. Let's take a look at the header file here because I need the types for the renderer and the texture. And I've also created here what I've called a buffer. And what this is just an area of memory where we're going to get and set information that's going to relate to pixels. And we're going to actually then use that memory to write to the texture, which will pass to the renderer, which will display on the window. So there's like a chain of 3 different things here. There may be a simpler and better way of doing this, but this is a way that definitely works and it seems reasonably efficient. So this is the way I've kind of settled on, but you may find a better way of doing this. It's possible. So let's go to screen.h here, and in screen.h somewhere, this is still screen.cpp, so we need to go down here. Here's my renderer, texture, and buffer. So let's create those objects in our main file first of all. So I need to go to the right project here that I've just created, main.cpp, And somewhere before we actually use these, I'm going to have to create a relevant object. So let's maybe do it here. So I need a SDL underscore renderer pointer, and let's call that renderer, and we need to set that equal to the return value of our create renderer function, which is somewhere down here. Let's take a look. So here we are, SDL create renderer. Let's type that out. So SDL underscore create renderer. And what arguments do we need to pass to this? Well, let's take a look. So that the first argument is the window that the renderer is going to render into. Let's type that. So we've called that just window, the pointer to the window. The next argument is -1, which if we look at the documentation, well, let's do that in a second, because at the moment we've got a syntax error that prevents the documentation showing, or you could just paste this into Google. And the last argument I figured out by looking at the API document, that's SDL renderer present vsync. So I'm going to copy that. And what this does is it ensures that our rendering is synchronized with the vertical refresh of the screen. So your computer screen is going to refresh a certain number of times a second. Like, I don't actually know how many. Let's say it's 30 times a second, 50 times, I'm not sure. And it refreshes from the top left-hand corner. It goes across the rows and moves downwards. So it redraws the screen from the top left, goes right across to the top right, and then it does the next row a bit further down the screen, going from left to right again. And if you try to draw something to the screen when a render is in progress, like it's halfway down, you see something called shearing, where it's this kind of effect where you see sort of flickering on the screen, and there's a visible line that flickers somewhere across the screen horizontally. We want that not to happen, so we want to make sure that our rendering is synchronized with that refresh, so that we don't try to render to the window when the screen's actually refreshing. And at least on my machine, adding this flag here to create renderer seems to synchronize properly, and it prevents shearing. If we look at the create renderer documentation here, then we see the first argument is our window. The second one is just -1, just to say that we want to just initialize the first rendering driver available, whatever that is. I'm not really sure. And but it's basically a kind of default option there. And the last one, as I say, I found out by looking at the API document, by putting this function name into Google. So that's our renderer created. And let's go back and see if we can create a texture here. So now we need SDL underscore, I think it's texture pointer. I quite like having that asterisk next to the actual variable, so I'll put it there. So a pointer to an SDL texture, which I'll call texture. So this is the thing that the renderer is going to render, and which we're going to write our pixel information to. If we take a look at that, then again, quite complicated arguments, but we'll go through them bit by bit. So we've got SDL underscore create texture, SDL underscore create texture. Let's put the semicolon and the brackets in there. First argument is our renderer. So let's put that in, renderer. The second argument here is, this can be a number of possible arguments, a number of possible constants, depending on how many bits, how many bytes, basically, you want to represent one pixel. So I'm going to use this SDL pixel format, RGB 8888, which uses 1 byte for each pixel. So that means for each pixel, we've got we can select one of 0 to 255 different shades of each color. So each pixel actually uses 32 bits or 4 bytes. 3 of those bytes are going to represent the color information of the pixel, red, green and blue. And each red, green and blue value can have 0 up to 255 different possible values. 255 is the maximum value we can fit in 1 byte if we flip all the bits to 1. The other value here, A, stands for alpha, which is basically a transparency. We won't be using that, and I've read lots of reports that doesn't work in SDL, and that seemed to be my experience. But actually I think that you can set various flags here and there to various functions to get that working, but I'm not going to make use of it in this tutorial in any case. Let's take a look at what's next. So now we've got SDL texture access static. Now this has to do with the way that we're writing to the texture. I can't really remember the details of this, but basically we want to take a load of memory containing values for each pixel and write them directly to the texture every time we go around this loop, and that flag enables us to do that. So let's put that in. And finally we've got the screen width and the screen height. So let's just copy those. We've already got these constants defined in our program up here, so we can put those in because the texture needs to know how big it's going to be. Let's format that. So we've got our texture and our renderer. We also need to remember to deallocate the resources allocated to those. So I've done that in my final program in a method called close. So here we're using SDL destroy texture and SDL destroy renderer. So let's go ahead and put that in. We destroy the texture first because it's using the renderer. So we probably should destroy that first. Otherwise we're going to have if we destroy the renderer, then we're still going to have a texture that's using that destroyed renderer. I'm not sure if that matters, but it's prudent to get them in the appropriate order. Let's say SDL destroy renderer, and after that we can do SDL destroy texture, and pass in texture. Hopefully that should do the trick. It's probably a good idea to check if these are null. Let's take a look at the documentation and see if it says anything about returning null. So I've just searched Google for the function name here, and so it returns null if there was an error, and we can call SDL get error as well. So we could check that. It's probably prudent to do so. Let's say if renderer is equal to null, then if you don't check it, then your program's basically just going to crash if this doesn't work properly. Let's say cout could not create renderer endler, and let's just return some non-zero integer to signal an error. And let's say if texture equals null, whoops, got my caps lock on here, then cout could not create texture endler, and then I'll return some other value. Could just return naught here. As I said previously, it doesn't really matter. If we could create the window but not the renderer, we probably in either case we should probably call SDL quit like this. If we could create the window, so by this stage we have created the window, so we should probably put destroy window in here as well. Let's put destroy window before we call SDL quit. If we are able to create the renderer but not the texture, we should probably destroy at least the renderer. So at this point, by this point we've created the renderer but not the texture. So let's destroy the renderer. Now this is a lot of repetition of code. We could refactor this, and perhaps I will in the final tutorial, because I don't really like or like in a later tutorial, because I don't really like having multiple calls to the same functions in here. We could have something that sort of checks if any of those are null and destroys them if they are not null later on, rather than repeating all this stuff. But we'll leave it for the moment, because the object for the moment is just to get a basic program working, even if it's ugly, that demonstrates the basic principle, and then we can refactor it and make it more elegant. So we've got our renderer and our texture. There's another thing that we need now, which is we need some sort of area of memory that's big enough to hold the information for all the pixels on the screen, because we're going to take that memory and we're going to basically write it to the texture. So we're going to update the texture with that information. And what I'm going to use is this type uint32. So I'm going to say here uint32 pointer. Now what is uint32? This is a type declared by SDL, which on most systems will be equivalent to an int. An int is usually 32 bits, but it's possible that on some systems, because C++ is not absolutely standardized, that an int might not be 32 bits, could be something else. So for that reason, SDL have defined this type, which is guaranteed to be 32 bits, but it's basically an int. And we want to allocate enough of these for all the pixels on the screen. Because if you think about it here, so we've got, for each pixel, we've got 4 values, red, green, blue, and alpha. Each of those is 1 byte. So for every pixel, we've got 4 bytes, which is 32 bits. 4 times 8 is 32. So for every pixel, we need an int size, a 32-bit bit of memory to represent all the information that's going to be in that pixel, all the colors of it basically. So we're going to allocate enough memory for all the pixels on the screen, and each one's going to require 32 bits. So let's say here, I'll call it buffer. Buffer just means an area of memory basically, equals new uint32, and the amount of memory that I have to allocate is going to be screen width times the screen height, because it's just, the screen is just a rectangle, which is screen width pixels wide and screen height pixels high. So that's our buffer, and we must remember to free this later on as well. So let's go down here and say delete, and we need the array brackets because it's an array that we've allocated there. Delete buffer. Okay, so that looks good. Now you might wonder what happens if memory allocation fails. Some C++ systems new will return null at that point, and we can actually configure new to make it do that. But by default on most systems it will raise an exception. We haven't looked at exceptions. I'm saving that for my intermediate C++ course, which is probably coming next. But the bottom line is your program will crash, possibly with an error message, but it will crash, well, not really gracefully, but hopefully somewhat gracefully if we can't allocate memory at that point. The trouble is, because we're not doing anything with this exception, we then wouldn't be able to call these functions. But I'm not going to worry about this for this program. Ideally, we would check for that, but this is going to succeed unless your computer is incredibly tight on memory. If it's so tight on memory that we can't allocate 32 bits for each pixel on the screen, then probably a lot of programs are going to be crashing anyway. So this is kind of a justification of why I'm not checking this. But ideally, in a kind of professional program, ideally you'd probably check to see if that memory could be successfully allocated, although I'd be willing to bet that very many programs that are on sale do not check. But to be perfect, we really should. So I've allocated a renderer and a texture and a buffer that we need to contain all the information for the pixels, and I've freed all those resources as well down here. Now, what we need to do is we need to update the texture with the information contained in this buffer, which at the moment is just garbage. And I then need to tell the renderer to render, in other words, draw the texture. So let's look at how we do that, because I really can't remember, but I'm going to consult my final program again. So if we look at, I think, screen update here, here we go. So we need this stuff. So the first thing we need is SDL update texture. And eventually I'm going to move this into this loop so that we're updating the texture every time this loop occurs. But for the moment, I'm just going to put it above this loop. Let's say SDL underscore update texture. Let's check what we do with that. So the first argument is the texture. So we pass in our texture. Second argument is null. We'll take a look at what this is in a moment. Then we pass in our buffer so that's containing the information that we want to update the texture with, or it will do once we've set that up. And then we pass the pitch. The pitch is the number of memory allocated to one row of pixels. So if you think about what that is, it's going to be screen width. That's the number of pixels multiplied by size of uint32, which is 4 bytes, or we could just pass in screen width times 4. Someone seems to be sawing something in the background. I apologize for that, but anyway, I'll carry on. So if we look at the documentation here, so we've got the texture is the first argument that we need, and the next argument is null if we want to update the whole thing. And then we've got the raw pixel data that we want to update it with. And finally, we've got the pitch, which is the number of bytes, it says, between rows of pixel data. In other words, the number of bytes per row of pixels. I'm not really sure why it says between, but if you want to go from one row to the next, this is how many bytes you have to add on. It's possible, if we'd allocated some really strange size for the window, that we might have extra bytes at the end of a row of pixels that aren't actually used for rendering, and then maybe the pixel will be different to the number of pixels in a row, but that's not the case here, so this seems to work fine. So we update the texture with the pixel information contained in this buffer, and the next stage is we clear the renderer. So let's call SDL underscore renderer clear, I think it is, or render clear, and pass in the renderer. Something wrong there, maybe it's render clear. Okay, there we go. Then we copy the texture to the renderer. So let's do that. So SDL underscore render copy. First argument is the renderer, then the texture, then null, and null. And what are these? I don't know. Well, the renderer and the texture obviously are the renderer and the texture. And then we've got null, and that's the first null is to specify that we want to use the entire texture, and the second null is to specify that we want to use the entire renderer. And finally, I think we've got render present. So we've got SDL underscore render present. And this is basically, it's just actually doing a render. It's presenting a renderer to the window. It's actually rendering it. So we're copying the pixels to our buffer, then passing the buffer to the renderer after clearing it, and then we're presenting the render on the screen. Now, if I run this, the results are going to be a bit random. Let's try running it, see what happens. Whoops, that's the wrong thing. That's my final program. Let's try this. So I'll go to project, build project, and we'll run it. So it's just black. it would not have surprised me if we'd seen a load of garbage in there, because when we allocate this memory, it's going to contain just whatever happens to be in that memory that was allocated. And it seems that for me, this time at least, there's nothing in that memory, so it's just blank. But there easily could be something in that memory. What we want to do now is we want to write some pixel information into this buffer so that we can see something happening on the screen. I'm going to use a very, very, very useful function which everyone should know about, called memset. Memset allows you to set a block of memory with a particular value. So the first argument is the buffer. The second argument is the value that we're going to write into every byte of that memory. So let's put 255, because we want to try to get every byte set equal to its maximum value, red, green, blue and alpha, and that should give us a white colour. And then, if I remember rightly, we need the number of bytes that we want to set, which is going to be, screen width times screen height, the number of pixels, times size of in bytes, u int 32. So hopefully I've got this right. We're going to write the maximum value that we can put in a byte in every byte in all of these bytes. And memset is a very quick function, which is one of the reasons it's very, very useful. So let's try that and see what we get now. So now we've got a white screen, which is what we wanted. Now another way of representing 255, which I'm going to be using in this tutorial rather than 255 probably for the most part, is we can write this in hexadecimal. So hexadecimal is it's another number system like binary, like the familiar decimal, where we use each digit can have one of 16 possible values, starting at 0 and going up through 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we supplement some extra values by going A, B, C, D, E, and F. So in hexadecimal, 255 is 0xFF. The reason this is particularly useful, well, by the way, OX is just a prefix in C++ to say this is a hexadecimal value. And the reason this is really useful is because we'll see later on that if we want to pack multiple bytes into one single uint32 value, a 32-bit int, then we end up with just 2 digits per byte in the hexadecimal system, which means it's easy to see which byte represents what in the final integer that represents the colour of that pixel on the screen. I'll go into that later on, but that's basically the advantage of it. We need exactly 2 digits here to specify 1 byte, and if you're packing bytes into an int value, then it works out that it's very easy to see which byte corresponds in our case to which colour, but we'll get onto that later. So 255 in hexadecimal is FF, like that. Let's just run it again, check that it still works. So that looks really good. Probably in the next tutorial, what we'll do is, there are several things to do next, but basically we need to deal with pixel access next, and we're probably going to do that in the next tutorial. We also need to think about the colours, how we're going to devise what colours to draw on the screen, and I might do that in this basic program as well. But if you look at this program now, this is a big main function, and we could carry on like adding stuff to this, but by the end it would be really huge and not easy to understand. We could split this up into multiple different functions. That's kind of C-style programming. But what we're going to be doing is splitting this up into classes, but we're going to continue working with this for the moment, because before I want to refactor into classes, I want to just make sure we've got a little demo program, and it is still quite little really, that just demonstrates all the basic things that we need to do, and then we can proceed forwards in confidence. So we'll probably take a look at pixel access and possibly colours in the next tutorial.